Thank you. Yeah, first of all, thanks to the organizers for setting up this conference and the associated program, and yeah, you know, the opportunity to be here in this wonderful place and present some of my work. I want to talk about competing orders in twisted bilayer graphene, and more specifically, I added something to the title. I want to talk about twisted bilayer graphene at charge neutrality and what this might have to do with quantum critical Dirac fermions. Sorry. Now, before going into details here, let me try and connect to yesterday's talk, at least roughly. As you all know, there is this ubiquitous non-Fermi-liquid regime in many of the correlated metals that we study, and this includes twisted bilayer graphene. There seems to be a connection to a putative quantum critical point at zero temperature, but theoretically it's kind of challenging to describe that metallic quantum criticality because we have a Fermi surface, and that Fermi surface provides us with an extensive number of zero energy modes. And this basically makes it difficult to find a well-defined theory for quantum critical metal beyond a self-consistent one-loop approximation. Now, there is, in a sense, a minimal model for this type of fermionic quantum criticality if we consider the chiral phase transition in a two-dimensional Dirac semi-metal, where we gap out the Dirac fermions if the interaction is large enough. And in that case, this extensive Fermi surface shrinks to just a point, so we kind of get a handle on these zero modes from the fermions. Furthermore, it's been shown that there is emergent Lorentz symmetry close to this transition, and this makes it theoretically, nicer to describe. And in fact, there is a well-defined theory for this quantum phase transition. You can describe it within the so-called Gros-Neveu model, and it leads to the chiral ON universality classes. And here the situation is really, in a sense, on a different level. We're not discussing qualitatively what is the quantum critical metal here. In fact, it's a semi-metal, but there is already agreement emerging on the quantitative side. What are the critical exponents that characterize this phase transition between, across different methods? And well, this is of course theoretically very nice, but then of course the direct question is, what about experiment? Can we observe this? And so far I would say it's not yet clear if this has been seen or can be seen somewhere. But I think there is a hot candidate, and this is twisted bilayer graphene, because here we do have Dirac fermions at charge neutrality, and in fact they are protected by a certain C2T symmetry, and because of the twist together with interlayer tunneling, we can in fact tune the velocity of these Dirac fermions, and as you all know, close to a magic angle, this velocity vanishes.
Could I just make a quick comment?
Sure.
In an actual experimental system, that symmetry may not be there because of boron nitride. It's a well-known secret among the experimentalists at the Dirac point.
Well, I think they do see Dirac fermions if you go in the measurements.
Which experiment you're talking about? It's definitely not universal. This is a purely experimental point.
Well, we can discuss maybe later.
Oh.
I think it is a pretty good symmetry in these systems.
Boron nitride does make this.
But the question is on what scale, right?
Yeah.
So if there are Dirac fermions in the systems, which I think is very likely, then we can tune their Dirac velocity, and this effectively means that we can tune the ratio of interaction over kinetic energy. So this means that we might be able to tune across this phase transition, which requires a critical interaction strength. And in fact, several years ago, graphene itself, untwisted, has been estimated to be somewhat close to that transition. So it is conceivable that this more strongly interacting system of twisted bilayer graphene is on the other side as we approach the magic angle. Let me also mention that there are other Moiré systems where this might be possible, specifically twisted gamma valley transition metal like chalcogenides. Now again, what about experiment? Can we see this phase transition? And here the answer is not so clear because both semi-metallic and insulating behavior has been reported at charge neutrality. This might be due to extrinsic effects, in fact strain or the substrate, as well as disorder play an important role. However, in ultra-low strain samples, a gap has been seen. Furthermore, there is an intrinsic effect that leads to this strong sample dependence, and that is an approximate U4 or even U4 cross U4 symmetry in a certain limit. And because of that, there are almost degenerate ground states which all have similar energy, and this has been investigated in an impressive, extensive number of works, mainly within self-consistent Hartree-Fock theory. But of course, if you have such a situation with many ground states close by in energy, there's another intrinsic effect which is important, and that's the interchannel feedback, so the competition of these order. And this is what we wanted to understand and study, always having this question in mind, which possible critical transition exists here. So this is the rough plan of the rest of the talk. I want to introduce our Dirac fermion model for twisted bilayer graphene, and then discuss the effect of this interchannel feedback if we have such an approximate U4 symmetry. And I'm going to show to you that this will render some of these transitions inaccessible. Let me also acknowledge the person who really did the work here, Nikolaos Parthenios, who is a PhD student in Stuttgart/Munich, and the credit really goes to him for what I'm gonna be presenting. Okay, so with that, let's go into the model. First of all, let me stress that we are basically taking the low energy limit of a low energy limit. If you look at twisted bilayer graphene, it has these spaghetti of bands, but the interesting physics we are always discussing happens if we zoom in here to the narrow bands around the Fermi energy. These are isolated bands, you see them here, and if we then zoom in even closer around charge neutrality, around the Fermi level at charge neutrality, this is where we would find the Dirac electrons. Then if you want to describe these Dirac electrons, you can write down the usual Dirac action, a Lagrangian, and here several different degrees of freedom are important from twisted bilayer graphene. First of all, we have the original valley and sublattice degree of freedom from the graphene lattices, and this is what forms our Dirac algebra. And then, at least trivially, in the kinetic energy, the spin appears and the so-called mini valley, which tells us that we have basically two flavors of these Dirac fermions with the same chirality in each of the original valleys K and K prime. Because we are considering this low energy limit, there are emergent symmetries. On the one hand, we now have a full rotation symmetry, not just C3, as well as emergent particle hole. But there's another symmetry, which I'm going to call flavor symmetry, that goes back to which of basically the Pauli matrices commute with our Hamiltonian in the Dirac language. And first of all, there is this SU2-like manifold, which comes from basically the valley degrees of freedom. But then, because we have the spin, this can be enlarged to SU4 with these generators. If I had the mini valley, it would be SU8. And then, at least theoretically, we can keep going, and we generalize this to general fermion flavor numbers so that we have an SU4 and F symmetry. Assuming these symmetries, you can write down all symmetry allowed couplings, and in this case there are 6 of them, which I'm showing here. But we can also reduce that symmetry to SU2 and F cross SU2 and F course U1, because keep in mind that this is a low energy theory, and the original model might have this symmetry broken to this, so this can appear in the interaction in principle. The couplings I'm writing down here, in fact, form a fields-complete basis, and in that sense, you cannot find any other thing, and it's a universal low-energy model. Good. So this is what we wanted to study, the interchannel feedback, if you have all these couplings. But first, let me do something simpler. Let me assume we have just one of them. For example, it could be this one, which, if I have just this one, I can resum it in an RPA-like fashion, so mean field approach, and then I would get a renormalization of that coupling, which has an instability if this becomes 0. And for that to happen, I need to overcome a certain threshold coupling, which is what we saw earlier in the phase diagram. In this particular case, for the G4, the instability is towards chiral symmetry breaking, and in fact, it's towards an interaction-induced quantum anomalous Hall state. Now, in this way, considering each of the couplings separately, I basically can identify the ordering tendencies that correspond to each of these couplings. So let me quickly just give you an idea via examples what these correspond to. And depending on the people you ask, you'll have different names for that, but yeah, just let me give you some examples. First of all, we have a density interaction, and then this quantum anomalous Hall state that I just described. This coupling V1 would correspond to a SU4 manifold of orders that polarize the electrons. So, for example, the Welle polarization or spin polarization, which we kind of heard about in a different system just now, would be in that manifold. Then we have a U4 manifold of insulators that gap the Dirac electrons. Certain intervally coherent states, for example, are in there. And then finally, we have orders that would spontaneously break rotation symmetry. And, all of them split into several subgroups if we then reduce the symmetry. Yeah.
There are also states people call TIVC and KIVC.
Right, yes. They are, so it depends a bit on, now this goes into details, but on the mini-Welle degree of freedom. Here I'm just assuming unity, but their dependence is hidden in these fields transformation. So if we have the unity, this would be the TIVC, and this would be the KIVC. But of course, they are related. If you add some mini-Welle Y Pauli matrix, this might switch. All right. So now we've seen that each of these couplings separately could induce an instability. But as I mentioned, we want to see what happens now if all of these channels talk to each other. And to do that, we use renormalization, perturbative renormalization group approach, which in a sense gives us an unbiased decision on the fluctuation-induced instabilities. And in that case, the renormalization of the couplings, can now depend on all of the other couplings. And in fact, the details is not important here. I'm showing you the simpler case of these RG equations. You see that all of the couplings couple to all of the couplings. So these are non-diagonal. But if I now go to the large NF limits, only these encircled terms survive. And you see that these are diagonal now in the coupling. So in that way, I go back to the single channel mean field resummation. So NF kind of gives us a handle on the interchannel feedback, the importance of that interchannel feedback. And you can see this also here. I'm plotting an example of these critical couplings as function of NF, and in fact, at small NF, all of them become non-zero. Good. So now, more generally, we want to study the possible instabilities, and then in the RG approach, these are connected to fixed points, and We are interested in stable fixed point, which we can relate to quantum critical points. And here again, I'm showing an example of the G flow where you see two of these fixed points in red for the couplings G4 and V4. And what you also see is that these fixed points basically set the threshold of these minimal coupling that's needed to induce the instability. And if you increase the bare interaction beyond that, you see that there is a flow to strong coupling. So the renormalization of the coupling is so strong that it diverges, signaling the tendency to form bound state and break the symmetry spontaneously. Good. So what we did is then get an overview of all the possible fixed points we have here, and then study them as function of this NF to see what happens when we turn on this interchannel feedback. And we found that it's something, I guess, well known, but we found that these large NF mean field solutions can disappear, and they can do so in several ways. First of all, the solution might just disappear as function of NF, so move into the complex plane. Another option is that the fixed point becomes unstable, which would mean multi-critical, so we have more than one relevant direction here. We can calculate this by looking at the second largest critical exponent, and that would change sign when this happens. So we see that due to this interchannel feedback, some of the transitions are not accessible if we go to small nf, which is the important regime for twisted bilayer graphene.
Just make sure I understand, your RG matrix is always one loop.
Yes, yes,
one loop,
yeah, this is
for arbitrary NF. You're just going to analyze the one loop.
yes, okay. Simple perturbative Wilsonian approach. Okay, then on top of that, we want to identify which instability corresponds to which of these fixed points, and for that we check the susceptibility for each of them within linear response. So what you do here, you add kind of a test field, and when you send that test field to 0, you check how the susceptibility responds. And then the susceptibility might diverge, and we identify the ordering tendency with the one that has the most divergent susceptibility. Good, so with that, let me give you an overview of what we find. In this SU4NF case, there are 7 potential instabilities. 6 of them correspond to this single channel large NF solutions. 7th one appears at smaller NF. Out of these 7 potential instabilities, 3 have emergent Lorentz symmetry. And if we then go to these small values of NF, where we have twisted bilayer graphene, we find in fact that 2 of these 7 solutions do not have a divergent instability, so they don't correspond to such a quantum critical point. 1 is unstable, and 2 disappear, which leaves us with just 2 possible solutions. One is this quantum anomalous Hall state that I just mentioned, and the other is the SU4 manifold of states that introduce a gap in the Dirac spectrum. So this indeed might give us a chance to observe this quantum critical point. Good, then on top of that, we can look at the generalized case when we reduce that symmetry. Here we have 18 single channel large NF solutions, and we can follow them down to smaller NF. Furthermore, we can check these previous fixed points for the higher symmetry case. In that case, we find there is no emergent SU4, so this is a relevant perturbation. And we still find that these instabilities towards insulators remain the most stable. There's one exception. So, furthermore, a state that simultaneously polarizes spin and valley now becomes stable in this lower symmetry case, and certain other instabilities towards spin polarization, IV's intervally coherent orders or spin nematic order also benefit in the sense that their critical NF is reduced quite extensively. All right, so this brings me to the end. Let me summarize what I've told you right now. We've studied these possible quantum critical transitions in a Dirac fermion model for twisted bilayer graphene or other moiré materials that can be described by such a Dirac action. And I've shown you that this interchannel feedback is important in such a situation where we have nearby a competing state due to this larger symmetry. Within this approach, instabilities towards gapped phases are the most stable, and I guess that makes sense because they can gain the most condensation energy. I think our study also raises interesting other questions. For example, what about the quantum critical behavior besides these well-studied chiral ON symmetries corresponding to some of these fixed points we found? What's the role of external effects like strain, disorder, etc. in this analysis? And then, of course, finally, what about finite temperature, finite chemical potential, which will be very important if we want to compare to experiment. Thank you.
Yeah, thank you very much, Laura. Questions? Yes?
Since you spoke of Dirac points at charge neutrality, there is an old story going back all the way to Abrikosov and Beneslavsky, who pointed out that because of small density of states, Coulomb interaction is very poorly screened, and its effects are very strong, and qualitative rather than quantitative. Does this enter your picture at all?
Right, so one effect of this is that you need this, because your density of states goes to 0 at the Dirac point, you need this finite coupling strength to induce the instability. And then the other question is basically about the long-range versus short-range part of the potential. And at least for these chiral ON models, it's been shown that the long-range part is marginally irrelevant.
Thank you.
I have a question about the critical, I'm here. Hey, about the critical number of flavors in your theory. So these are some interesting fractional numbers, but do they stem from some internal structure of the theory of interactions of polarization operators, or they are somehow dependent on finer details?
I'm not sure if I understand the question. So how this enters is in the loop. So that would be the internal structure.
No. So
generally, these are non-universal numbers.
Okay, so they're non-universal, and what do they precisely depend on in your model? The initial couplings, or? No, just. So these are just literally fixed points, what you end up with?
Right,
okay.
Yes.
Okay.
But, yes,
yeah.
But they would, I guess, yeah, okay. They would change with the model, I guess.
Oh, did you consider any superconducting order parameters?
No, we did not yet. I think that would be also interesting, although I think that because you need this finite threshold and of course of interaction strength, and of course if you want superconductivity at least from repulsive interactions, it is kind of difficult to get this with a zero chemical potential. So there it might be useful to go to finite chemical potential first.
Just for me to understand better what the control of the calculation is. So the short-range interaction is marginal, is irrelevant for this problem, right?
At least for so this has been shown explicitly for the states that get the Dirac points, not for the ones that do not get it.
But, so these 6 points then are, unless you are in the large n limit, they are of order 1 in your coupling constants, right?
No, actually, I think the numbers are smaller. Let me go back.
But they're finite threshold.
But they are finite threshold, yeah.
So why would I want to trust them?
Well, yeah, okay. So this is controlled within weak coupling, but we do find fixed points which are within weak coupling. So these are dimensionless numbers, and you see that they arise.
So they are numerically of order 1, but they happen to be small?
What do you mean numerically at order 1?
I mean,
because this is, 0.01 numerically.
Yeah, but 1 over 2 pi squared is also of order 1, and it's very, very small compared to 1.
Yeah, okay. Yeah. I would say this is
analytically of order 1, numerically small.
Okay.
So they are not, numerically, they are not close to 1.
Yeah.
Any other questions? All right, then let's thank Laura. Thanks again.